Hello, my name is Alex with AlphaStar Academy, and today we are going to be covering the problem Farmer John Actually Farms, question number 3 of the Bronze 2023 USACO exam in December. So the problem summary is quite simple. We have n different plants that are growing at different rates. And we want to find the minimum amount of time so that the height of each plant follows a particular ordering given by the problem. So maybe the problem wants plant 1 to be shorter than plant 2, which is shorter than plant 3, or maybe the problem wants plant 3 to be shorter than plant 1, which is shorter than plant 2. It changes depending on sort of the test case. Sometimes, however, it's impossible to achieve the ordering they've specified, and in those cases, we want to print -1. So let's take a look at a sample here. So we have two plants. We have plant 1 and we have plant 2, and we have a couple variables associated with each plant. So the H variable is its initial height. So plant 1 is initially height 4, plant 2 is initially height 1. A is the rate at which they grow. So plant 1 grows at a rate of 1 unit a day. Plant 2 grows at a rate of 2 units a day. And then this value T establishes the ordering between plants. So one important property is every single T value is distinct, and they range from 0 to n-1. And the value T just means that I want T plants to be taller than the given plant, right? So plant 2 has a T value of 0, so that means I want 0 plants to be taller than plant 2. Another way of saying this is that I want plant 2 to be the tallest plant. The T value 1 here means that one plant is going to be taller than plant 1. This means I want plant 1 to be the second largest plant, right? So you can convert these T values into sort of this ordering by just considering them in reverse. The plant with the smallest T value is the plant you want to be the tallest. The plant with the largest T value is the plant you want it to be the smallest, or the shortest rather. So we can simulate the growth of these plants and figure out sort of how long it takes for plant 2 to finally be taller than plant 1. Because right, plant 2 starts shorter, and our goal is to make it taller, right? So we want no plants to be taller than plant 2, but currently plant 1 is taller. So after 1 day, plant 1 will grow by 1 unit, and I'll just use numbers to mark sort of the growth rates. So this is day 1. Plant 1 has grown 1 unit, plant 2 has grown 2 units. Now let's look at day 2. Plant 1, again, grows 1 unit, so it's now grown 1, 2. Plant 2, on the other hand, grows 2 units. All right, so now we're going on to day 3. So plant 1 grows another unit, and plant 2 will also grow 2 more units. And now they're tied, right? So they're the same height, but that's not sufficient. We want them to be different heights. In particular, we want this to be strictly bigger than plant 1. So we go into day 4, we see that plant 1 grows by another unit, and then plant 2 grows by 2 units. And finally, plant 2 is taller than plant 1, and we can see this took 4 days. So our answer would be 4 for this particular test case. And there's several different ways we can approach this problem. So one way of approaching the problem would be simulation. And that's basically the idea of what we did above, right? So we loop over all of the days. This is a little fuzzy point, right? How do you classify all of the days? Because you could just go on forever. Then you loop over all of the plants, and then you increase all of the plants by their particular growth rate, and you check for that day if the ordering is correct. So you loop over all the plants, and then you check if the ordering's correct. And this is the runtime of this is going to be like the maximum number of days required times n. And you should always ask yourself whenever you have an algorithm idea, is this fast enough? And here we can see in the problem statement, n is 2 times 10 to the fifth, also known as 200,000. So a pretty big number. So if the number of days is large, then we might be concerned that we'd run out of time. So what is the maximum number of days? Well, we'd have to look at sort of the size of the values here. And we can see that HI ranges from 1 to 1 billion, and AI ranges from 1 to 1 billion. So sort of in the worst case, the max number of days is going to be approximately 1 billion. So if I take 1 billion and I multiply that by 200,000, I'm pretty certain I'm not going to pass very many test cases in that case. So you could scroll down to the scoring section, and you can actually see that they do have a series of test cases where the simulation method does pass. So you're going to probably pass test cases 4 and 5, because in these test cases, they guarantee that AI and HI, which sort of determine the max number of days, are small. So if AI and HI are small, then we think that this simulation approach will work. Unfortunately, that's not very many test cases, right? 5 out of 13. We probably want to shoot for a little bit more than that. So we need a new idea. If like the naive simulation strategy doesn't work, what can we do instead? Well, the right idea is a little bit hard to jump to, but the idea is that we don't need to go step by step looking at every single plant's growth rate. So we loop over all the days, increase the growth rates, or increase the heights, loop over all the days, increase the heights, right? This could take a really long time. Instead, we should see maybe if we could jump into the future where all of the growth rate, like we find the value of t, that's sort of the perfect value of t, right? So we find the value of t where it's the first value where the ordering's obeyed, and maybe there's a math formula that we could work out that's a little that skips this simulation step where you have to go day by day. And this would lead us to a sort of brute force solution where for each pair of plants, we calculate the minimum number of days required for that particular pair to obey the ordering, right? So the idea is this. Plant 1 has a t value, let's call it T1, and plant 2 has a value T2. If T1 is less than T2, that tells me that plant 1 has to be taller than plant 2 eventually. So my goal would be to calculate the first instance, so the first moment in time where plant 1 is taller than plant 2. And then across all pairs of plants, I save the max amount of time required to sort of correct that particular pair. And then once I've corrected all pairs, I loop over every single plant, increase it by this max amount of time required, and then check if it leads to a correct ordering. This is a better solution. It leads to an n squared runtime. Why n squared? Well, the problem is we're looping over all pairs of plants, right? So if you loop over all plants, that's going to be O of n. That's going to be a algorithm with runtime n. If I loop over all pairs of plants, then I'm thinking about n choose 2, or approximately an n squared runtime. And that's still a little bit too slow for this particular problem, because once again, n goes up to 200,000. So 200,000 squared, that's 4 billion, which is much greater than the 500 million operations that you generally get in a USACO question, right? That's a sort of weak heuristic for how many operations you get to use. It, of course, depends on the language you're working in. But yeah, so but you will notice that you pass more test cases than you did with the simulation method, because in test cases 6 through 8, it's guaranteed that n is at most 1,000. So 1,000 squared, that's totally doable. That's only 1 million operations. So we can be pretty confident that the brute force approach using looping over all pairs of plants would solve test cases up to test case 8. But we want to do better. And we want to pass over the plants once, right? So we can't afford to loop over all pairs. We have to go over the plants exactly one time. And the idea here is, suppose I have 3 plants. So I have plant 1, plant 1, plant 2, plant 3. So say I have these 3 plants, and they have the following t values. In particular, let's suppose that T1 is less than T2 is less than T3, right? This is a special case. This isn't guaranteed by any means, but let's just suppose that this is true. If this is true, that means plant 1 must be taller than plant 2, which has to be taller than plant 3. So if I check that plant 1 is taller than plant 2, and I check that plant 2 is taller than plant 3, then I know that I get this ordering without having to check the pair plant 1 is taller than plant 3, right? I don't have to check this pair of plants because I already know that plant 1 is taller than plant 2, and I know that plant 2 is taller than plant 3. So then I don't need to check that plant 1 is taller than plant 3. That's implied by the transitive property, right? So implied by transitivity. So if I don't need to check this pair, that saves me a step. And this gets even better with the more plants I have, right? So if I have, say, instead n plants, and I know that T1 is less than T2 is less than Tn, then all I have to check are the adjacent pairs of plants. So I check plants 1 and 2, then I check plants 2 and 3, then 3 and 4, all the way up to the last plant. However, the problem with this, of course, is this solution, again, assumes that the plants are sorted by their t values, right? So this is not guaranteed to us by the problem. So if we take a look at one of the sample inputs here, so this is a single test case. The first row is a value. These are the h values. These are the a values, and these are the t values. As you can see, the t values are not necessarily ordered, right? So here, 1 comes before a 0, and then we can look at another test case where here, again, these are the h values, these are the a values, here are the t values. You can see they're not ordered. But that's okay, because we can sort them ourselves. So this is going to be our final solution idea here. We're going to sort the plants, and then we're going to apply the same mathematics that we had earlier, where we're going to sort of calculate the min number of days required for a pair to satisfy the ordering. And then we only have to look at the plants I and I plus 1 for all values of I, right? So the key idea here is if we sort the plants, then we can reduce the number of pairs we have to consider. So we still have to consider a lot of pairs, but we've reduced the number of pairs we have to consider from n squared down to only n, right? Because we're only considering pairs that have adjacent t values, right? So if I copied and pasted this, for example, I would so this would be like this would be one plant. Just so you can sort of understand the input, this would be one plant, this would be one plant, this would be one plant, and this would be one plant, right? So each column here is a plant. And what I would do is I'd compare this plant and this plant because they have adjacent t values. I'd compare this plant and this plant because they have adjacent t values. I'd compare this plant and this plant because they have adjacent t values. And I'd compare this plant and this plant because they have adjacent t values. So the key step here is sorting the plants so that I only consider pairs with neighboring t values. And Because this might be sort of a complex idea, let's run through the mathematics for ourselves. So we have a vision. Let's see if we can execute on that vision with a sample test case. So in this example, we're just going to work with 3 plants. And the plants are as follows. The first plant has height 1, the second and a growth rate of 5, and its t-value is 1. This means plant 1 needs to become the tallest plant. Plant 2 has a height of 17, it has a growth rate of 3, and a t-value of 1. This means it needs to become the second plant, or the second tallest plant, and plant 3 has a growth rate of 2, but its height is 100, right? So it starts out much, much taller than plants 1 and 2, but it grows slower. And eventually it needs to become the shortest plant. So maybe intuitively you can see that this test case is going to work, but the question is sort of what's the minimum amount of time we need in order to make it work, right? So we can see that because plant 1 grows faster than plant 2, grows faster than plant 3, if we just wait enough time, eventually this will be the tallest, this will be the second tallest, and this will be the smallest. But the question is, what is that time? How long do I have to wait until that's true? And note that if we didn't have these sorted, right? So if these didn't come in sorted, we could just sort the plants by their t-values on their own. And we're going to talk a little bit about how to do this. The best approach for sorting, I would probably use a technique called inverse indexing here. But it's a little tricky if you don't know inverse indexing. Especially if you're working in C++ or Java. But we'll talk more about how we actually sort the t-values at a later point in time. So let's look at sort of how we could go about calculating the minimum amount of time required for 2 plants to be of equal height. So importantly, we need to first understand the height of a plant. So that's this formula. It's pretty straightforward. The height of a plant at any given time is going to be hi, the height it started at, plus ai times the height of that plant. So, right, this is how much it grows each day. So, it's going to be hi plus ai times the number of days that have passed. Got ahead of myself there. So we're going to take hi, the original height, the growth rate, multiplied by the number of days passing, add those together, that's the height of plant I. All right, so the time required for the 2 plants to be equal then is given to us by t is equal to hi minus hj over aj minus ai. And you might ask yourself, where in the world did this come from? And the answer is quite simple, actually. It's pretty nice. It's just a little bit of algebra. So we're going to take hi plus ai times t. That's the height of the ith plant. Then we're going to take hj plus aj times t. And then we're going to solve for t. So we can bring the h's over to one side. Then we can bring the ai times t things to over to one side. And so we're going to have times t here, times t here. Then we're going to apply the distributive property to this side, right? So we have an aj being multiplied by t, and we have an ai being multiplied by t. So we're going to do hi minus hj is equal to aj minus ai times t. And we're going to continue on here. So what's the next step? Well, we want to isolate t, right? So this is the minimum amount of time for them to be equal. So we're going to divide by aj minus ai. So we get t is equal to hi minus hj divided by aj minus ai. And that's where this formula comes from. So hopefully that's clear. But this just goes to show that, math is important in these contests. And one thing that you're going to want to do if you're struggling with problems like these are get used to working with math formulas, really improve those algebra skills. They do come up in contests quite frequently. So now that we know how to calculate the time required for two plants to be of equal height, that's going to help us calculate the time required for two plants to for one plant to be just a hair taller, right? So the idea, let's apply it to these plants. So we're going to start off with plants 1 and 2. So the idea here, let's get rid of the calculations and then we can go through them from scratch. So for plants 1 and 2, let's plug in the values. So we have HI, so that's just H1. Then we have HJ, that's H2 is minus 17. And then here we have A2, that's going to be over 3. And then we have A1 is 5, so we're going to subtract off that 5. And we can see we get negative 16 over negative 2, which is going to be positive 8. I guess we could have flipped these around so that they're positive numbers if you like thinking in positive numbers instead. This is equivalent, right? So positive 16 divided by 5 minus 3, which is 2, gives us 8. So in order for plants 1 and 2 to become equal, we need 8 days to pass. How about for plants 2 and 3? So for plants 2 and 3, we need 100 minus 17, right? So that's going to be H3 minus H2 over A3 minus A2. Or sorry, A2 minus A3, so we get 3 minus 2. So that's going to be 100 minus 17 over 1, also known as 83. And these are the times required for the plants to become equal. So at time 8, plants 1 and 2 will be equal height. At time 83, plants 2 and plants 1 and 2 will be equal at time 8, and plants 2 and 3 will be equal at time 83. So how does this help us? Well, the key observation, all plants, so right, if we need 83 units of time for them to become equal, then in 84 units of time, plant 2 will be taller than plant 3. Or, sorry. Plant 2 will be taller than plant 3. All right, so let's see this for ourselves. And we can see the height of each plant at the end of time 84. Plant 1 is 421, plant 2 is 269, and plant 3 is 268. And you can see that plant 2 is just a hair taller than plant 3, right? If I decrease this by any number, we no longer have the ordering we desire, where 1 is the tallest, 2 is the second tallest, and 3 is the shortest, right? So 84 truly is the minimum value that I need in order for this ordering to be obeyed. And this is the key idea. So we're going to sort of sort the plants. Then we're going to loop over all adjacent pairs of plants, calculate this amount of time required to become equal, add 1 to the largest one of those, add that value to all of the plants, and then test if the ordering is valid or not. So if the ordering is not valid, we'll return -1. If it is, we'll return the amount of time we used. So let's transition over to the code. So I'm just going to take that over there. I'm going to move me over here, and let's take a look at the code. So I've already written the code here just because it's a little bit more of a complex program, but let's talk through it together and see the sort of techniques used in it. So the first thing we're going to do is we're just going to read in T. This is the number of test cases. So every single test case actually has multiple sub-test cases. And the idea is we're just going to solve the problem once for each of those sub-test cases. So we're just going to loop over all T sub cases. and print out whatever is the return value of this solution. So this is really the code you want to pay attention to. This is where we're actually solving the problem. We just return values from this function in order to solve each of the t-test cases. The very first thing we're going to do is we're going to read in our input. So we have an integer n. This is just the number of plants. We're going to read in h, a, and t, right? So this is the growth rate of, or sorry, this is the growth rate of the flowers. This is the original height of the flower, or the plants, I guess. And then this is that t value, which determines the ordering of the plants. And our goal is to create an inverse index. So in particular, we want to sort the plants from the lowest t value to the greatest t value. And there's lots of different ways you could do this. You could use an actual sorting algorithm, but that's a little advanced. We don't need something that complex. The easiest thing to do is just create a sort of data matrix that's going to store the height and the growth rate of each plant. But rather than indexing that data matrix by I, we're going to index it by ti. So that data I now stores the information of plant I with the ith smallest value of t, right? So if ti is 0, that's going to fill in the first slot. If ti is 1, that's going to fill in the second slot. If ti is 2, that's going to fill in the third slot, and so on. So data is now sorted based on the t values of the plants. And in particular, right, so the plants that need to become larger come earlier in data, right? So data 0 is the plant that needs to become the largest. Data 1 is the plant that needs to become the second largest. And then it goes down, so data n-1 is the plant that is the smallest. So the plant, and then we can move, is the plant that wants to become the smallest. All right. So hopefully the sorting of the data makes sense. We can now exploit that to loop over all adjacent pairs of plants and update this value t, which is going to store sort of the maximum amount of time I need in order for all of these plants to sort of obey their ordering. So the very first thing I'm going to do is I'm going to loop over all those pairs, and I'm going to save the values of data into variables named h1, h2, a1, a2. This is just for readability. If you want to use these data values everywhere, it's okay. But the idea is h1 is the height of the taller plant, right? Or it's the height of the plant that needs to become taller. So let's h1 is the height of the plant that wants to become taller. So if h1 is smaller than h2, that means some amount of time is going to have to pass in order for h2 to become lower than h1, right? So the goal is to eventually have it so that h2 is sort of less than h1. So this is our goal. But if this is true, then we have to wait some amount of time in order for this to become true, right? So we want the second plant to have a shorter height. Right now it has a taller height, so we're going to have to calculate some amount of time to pass. The problem is, if the first plant grows at a rate that is smaller than the growth rate of the second plant, then the first plant will never become taller, right? So if this is ever true, we can immediately return -1, because we know that this pair of plants will never satisfy our ordering, right? No matter how much the first plant grows, it's always going to be shorter than the second plant. And we're never going to lead to the case where finally the first plant's taller. All right, so however, if this is not true, then we can calculate this value of t, right? We're just using the same equation that we defined above, but we're adding 1 to it. Why are we adding 1 to it? Well, we're adding 1 to it, remember, because we don't want the time they're equal. We want the time right after they're equal, right? So the time where h1 finally exceeds the height of h2. And we're going to loop over all the pairs of plants and store the maximum. Finally, once we've stored the maximum, we're going to loop over all those plants one more time, and we're going to increase the height of the plants by the amount they grew, right? So this is just their growth rate times the maximum amount of time we needed in order to make sure that all of these pairs were satisfactory. And then we have to check. Now that we've adjusted all of those pairs in a way that we think should produce a valid solution, we have to stop and make sure it is actually a valid solution. So we're going to loop over all of those pairs one more time and make sure that those pairs have actually satisfied the fact that the ith plant has to be taller than the ith plus 1 plant. So if the ith plant actually ends up being the same height as the ith plus 1 plant or smaller, then we're also going to return -1 because that's another failing, right? If, however, they're all properly ordered, then we can just return t and we've solved the problem. All right, we're now gonna check the code and see if it works. So we're gonna upload it. AlphaStar.py, submit solution, wait for that grading server, and we'll see that we do indeed pass all of the test cases. So thank you for watching, happy coding, and good luck in your future USACO contests.